In this lecture video on probability, we'll be talking about the addition and multiplication rules. We begin the conversation by defining what a compound event is. A compound event is any event containing two or more simple events. The probability of A and B refers to the probability that A and B both occur at the same time as an outcome in a trial of a procedure. The probability of A or B is the probability that A or B or both occur as an outcome in a trial of a procedure. In order to understand the difference between and or, we can take a look at a Venn diagram. If this first circle represents event A and the second circle represents event B, then where they overlap represents where they both occur at the same time. In other words, where they overlap represents and. However, or is a little bit different. When we use the word or, we're including the event that A happens, B happens, or both at the same time. So in our Venn diagram, we would shade both circles and where they overlap to represent or. The formal addition rule gives us a way to calculate the probability of A or B. That's the probability that A or B or both occur. We want to include the probability of event A happening. We also want to include the probability of event B happening. But if we simply add these two together, that's the same as adding the two shaded circles A and B together, which includes the region where they overlap twice. In other words, we've double counted the region that's represented by and. So we can adjust for this by subtracting the probability of A and B occurring at the same time. Let's take a look at an example. Here we have the results from experiments with polygraph instruments. The results are broken down by whether or not an individual told the truth or told a lie, and if the polygraph instrument gave them a positive or negative result. We are going to find the number of people who had a negative result or told the truth. Notice that in this example, we are only calculating the number of people, not the probability. Let's first figure out the number of people that told the truth. If they told the truth, they did not lie. That would be these 15 and 32 people, for a total of 47 people. Now let's consider the number of people that had a negative result. That would be these 32 and 9 people in these two boxes, or a total of 41. If we simply added these two together to figure out the number of people that had a negative result or told the truth, we would get 89, and we would actually be very wrong. Notice that when we added these together, we double counted the people that did not lie and got a negative result. We are over by 32. Subtracting off that 32, we find that the result is really 57. Another way to look at this is a little more intuitive. We look at the table and find the people that told the truth, and we find those that had a negative result. Then we simply add up these three numbers. We have 15 plus 32 plus 9, which also gives us 57. Either way you look at it, the most important thing to notice here is to not accidentally overcount. We need to take into account any possible overlaps in the data. Now let's talk about some rules for complementary events. Remember that the complement of A is the event that A does not occur. So to calculate the probability of event A or the complement of A, we can use the addition rule that tells us this would be the probability of event A plus the probability of the complement of event A minus the probability of them both happening at the same time. But if these two events are complements, then it would be impossible for them to happen at the same time. So we simply do not need to subtract off this last part. And let's think about what this sum might be. We have the probability of A happening plus the probability of A not happening. That takes care of all possibilities, so this sum is equal to 1. And if these two things add up to 1, then that means we could find one of them by using the other. The probability of the complement of A occurring is 1 minus the probability of event A occurring. And the probability of event A occurring is 1 minus the probability of its complement occurring. For example, if the probability of rain is 30%, let's find the probability that it will not rain. You can probably figure this out intuitively, but let's use some proper notation. If we let A equal the event of rain, then the complement of A is no rain, or it not raining. We're told that the probability of rain is 30%. We can write that as 0.30. And now we can find that the probability of it not raining, or A's complement, is 1 minus the probability of it raining, or 1 minus 0.30, or 0.70. That's 70%. Let's find the probability that it will rain or that it will not rain. Think about that intuitively. The two options are raining or not raining, so that sum total should be 1. Writing this out, we have the probability of A or not A. That's the probability of it raining plus the probability of it not raining, which of course is equal to 1. We are certain that it will either rain or not rain. Now let's talk about the difference between independent and dependent events. Two events are independent if the occurrence of one doesn't affect the occurrence of the other. They have nothing to do with each other. Dependent events are the opposite. They are not independent. The occurrence of one does in fact affect the occurrence of the other. For the multiplication rule, we need a little bit of notation. The probability of A and B refers to the probability that A occurs in a first trial and B in a second trial. This second notation represents the probability of event B occurring after it is assumed that event A has already occurred. If events A and B are independent of one another, that is, the occurrence of one does not have an effect on the occurrence of the other, then the probability of event B happening after event A is simply the probability of event A times the probability of event B. However, if events A and B are dependent, that is, the event of A occurring does have an effect on event B occurring, we need to instead multiply the probability of event A occurring times the probability of event B occurring given that event A already occurred. Consider the following scenario. We have a jar of marbles. Inside that jar, there's 2 red, 1 white, 2 yellow, 3 green, and 1 blue. We want to find the probability of pulling a red marble and then a blue marble, but we will not replace the first before drawing the second. That is, we'll draw 1 marble, put it to the side, and then draw a second marble. So first, we have the probability of drawing 1 red marble out of this bowl. The probability of pulling a red marble is 2 out of 9 because there's 2 red marbles and 9 marbles total. Once that red marble is gone, the probability of pulling a blue marble is equal to 1 out of 8 because there's only 8 marbles left. So using the multiplication rule, the probability of pulling a red marble and then a blue marble without replacing the first is equal to 0.0278. Now let's look at this situation a little differently. This time, let's find the probability of pulling a red marble and then a blue marble if we do replace the first marble before drawing the second. We start the exact same way. The probability of pulling a red marble is 2 out of 9. There's 2 possible red marbles to choose from, and there's 9 marbles total. But after we draw this marble, we're going to replace it before drawing the second marble. So now the probability of pulling a blue marble is equal to 1 out of 9 because with that red marble replaced, there's 9 total to choose from. Now using the multiplication principle, we find that the probability of pulling a red marble and then a blue is equal to 0.0247, which is different than the first scenario. This is the difference between independent and dependent events. In the first scenario, those events were not independent, they were dependent. The probability of pulling a blue marble changed after we pulled the red marble out. In this situation, however, since we replaced the red marble, what we pulled first had no effect on the probability of drawing a blue marble second. Here we have 2 multiple choice questions, each with 4 options. If a person were to blindly guess on these, what's the probability that they would guess them both correctly? Probability of guessing the first question correct is 1 divided by 4, and the probability of guessing the second question correctly is also 1 divided by 4. Are these independent or dependent events? In other words, would the event of guessing the first question correctly change the probability of guessing the second one correctly? Not if this person is blindly guessing. So we can simply calculate the probability of guessing them both correctly by multiplying the probability of the first one correct by the probability of getting the second one correct. So we have 1 over 4 times 1 over 4, or 1 over 16. Let's look at some different types of examples. First, what's the probability that 2 people were both born on a Saturday? First, are these independent or dependent events? They are independent. Having one person born on a Saturday does not have an effect on the other person being born on a Saturday. So the probability of both of them being born on Saturday is equal to the probability of one person being born on a Saturday times the probability of one person being born on a Saturday. And the probability of a person being born on Saturday is 1 in 7. So we have 1 over 7 times 1 over 7, or 1 over 49. In decimal form, this is equal to 0.0204. For a different question, let's figure out the probability that 2 people are both born on the same day. This time, instead of specifying that 2 people are both born on Saturday, we are looking for the probability that they're both born on simply the same day. To calculate the probability of them both being born on the same day, think about the first person. What day do they need to be born on? It actually doesn't matter. The first person can be born on any day of the week. But once we know what day that person is born on, it changes the way we look at the second person. We need to know the probability of that second person being born on the same day as the first. What's the probability that a person is born on any day of the week? 1. And what's the probability that the second person will be born on the same day as the first? 1 in 7. No matter what day the first person is born on, the probability that the second will be born on that same day is 1 divided by 7. So here we have the probability of 2 people being born on the same day as 1 divided by 7, or 0.1429. Hopefully it makes sense to you that the probability of 2 people being born on the same day is a lot higher than the probability of 2 people being born on Saturday. And that concludes this lecture video on the addition and multiplication rules for probability.